In this video here, we're going to take a look at finding angles between lines and planes. Now, in the previous video where we introduced the scalar product, we saw how we could use the scalar product to easily calculate the angle between two vectors. So now for this video here, we want to investigate how we can find the angle between a line and a plane. So to get us started then, what we're going to do here is introduce a new way to represent the equation of a plane. And we call this the scalar product form of the equation of a plane. So what does that look like then? Well, the scalar product form of the equation of a plane is given as r dot n is equal to k, where k is equal to a dot n for any point in the plane with position vector a. So this here then is an alternative way that we can denote the equation of a plane. And as you can see, then we call this the scalar product form of the equation of a plane. So this here is probably an easier way to work with the equation of a plane. And you will see this quite extensively then as we work through the remaining topics here within this chapter on vectors. So to get us started here then, let's just take a look at how we find the angle between a line and a plane. So the acute angle theta between the line with this given equation here of r equals a plus lambda b and the plane with this equation of r dot n equals k, well, that's given by the following result. So as you can see, then we obtain this result here. So sine theta is equal to the modulus of b dot n all over the modulus of b times the modulus of n. Now the b, well, this just represents the direction vector for this given line, and n just represents the normal to our plane. And also just notice here then, this equation for the equation of a plane, well, this is the new way now that we can describe the equation of a plane. This is the scalar product form, right? The equation of a plane. So you can kind of see straight away how we're going to be using this new form here for the equation of a plane. And then to finish with here, this is something that's quite unfortunate, right? But this result is not given in the formula book. So this result here, so sine theta is equal to the modulus of b dot n all over the modulus of b times the modulus of n. As I said, unfortunately, this result is not given in the formula book. So it's just one of those things that you just have to learn and memorize. Okay. So we're going to take a look at an example shortly then for the angle between a line and a plane. But for now, that covers everything here. So to conclude our introduction here to finding angles between lines and planes, we also need to be able to find the angle between two planes. So we didn't actually mention this within the introduction, but again, it's just something that you need to be able to do here. So how do we find the angle then between two planes? Well, the acute angle theta between the plane with this given equation here of r dot n1 is equal to k1, and the plane with this given equation here of r dot n2 is equal to k2 is given by the following result here. So as you can see, then we get this result here. So cos theta, this is equal to the modulus of n1 dot n2 all over the modulus of n1 multiplied by the modulus of n2 here. Now again, just as we saw then for the angle between a line and a plane, this result here is unfortunately not given in the formula book. So again, just something that you need to learn and memorize and just basically familiarize yourself with this result here. Okay. But there we have it. We don't really need to say too much more here then for finding the angle between, two planes here, or the angle between a line and a plane. I think the best way to kind of demonstrate these concepts here is to take a look at some examples. So there we have it. That concludes our introduction here. So all we're going to do now is take a look at two examples here for finding angles between lines and planes. So let's get started here then with question 1. So what do we have for question 1? Well, it asks us to find the acute angle between the line L with this given equation here and the plane with this given equation here. So because we're looking to find the angle between a line here and a plane, we're going to use the following results. We're going to use here sine theta is equal to the modulus. We take the modulus here then of b dot n, and that's all over the modulus of b times the modulus of n here. Okay, like so. So clearly, to find this angle here between the line L and the plane here, we're going to take the sine inverse of both sides once we kind of evaluate this here. Okay, so in that case here, sine theta is equal to, we take the modulus then. So b here, that's my direction vector. So that's this I plus 2j plus 3k here. I've got I plus 2j plus 3k. And we dot this here with the normal to the plane. So that's this here. This is r dot n equals k. So n then is 3i plus 2j minus k. So 3i plus 2j minus k here, like so. And this is all over then. We find the modulus of b here. So to find the modulus of b, nice and straightforward, right? We simply do Pythagoras here. We get the square root then. I'm going to get, well, what am I going to get? I'm going to get 1 squared plus 2 squared plus 3 squared. Get the square root of 1 squared plus 2 squared plus 3 squared, like so. And then we times this here by the square root of, so I do 3 squared plus 2 squared plus minus 1 squared. So 3 squared plus 2 squared plus minus 1 squared. Okay, like so. And we take the modulus here of this full expression. So let's start then with the scalar products here within the numerator. So sine theta here is equal to, so 1 times by 3 here would give me 3. So we take the modulus here. So we get 3. We then do 2 times by 2. So that's going to be plus 4. And then we do 3 times minus 1, which would give us minus 3 there. Okay. And this is all over them. So what do we get here? So 1 squared plus 2 squared plus 3 squared here. So 1 plus 4 plus 9. What's that going to give me then? That's going to be the square root of 14, right? So we get the square root of 14. And same again here, right? So we get 9 plus 4, so that's 13, plus 1 would give us the square root of 14 here. Okay, like so. So if we simplify this here, then what do we get? So we get that sine theta is equal to, so clearly both my numerator and my denominator here will be positive, so we can drop the modulus signs here. They're not necessary. The 3's will cancel. I get left with 4 in the numerator here. We get sine theta equals 4. The square root of 14 times the square root of 14, that would just give me 14 there. So we get 4 over 14. Obviously, we could simplify to 2 over 7. So in that case then, if we just want theta here, which represents the angle between the line L here with this given equation and the plane with this given equation here, what we're going to do then is take sine inverse of both sides. So theta is equal to sine inverse of 4 over 14. So 4 over 14 here. So what do we get then when we put this into our calculator here? So what I get then, if I round my answer to say 1 decimal place here, is 16.6 degrees there. Okay, and there we have it. So that gives us the solution there to question 1. And then finally here, let's just take a look now at the very last question. So for question 2 here, it asks us to find the acute angle between the planes with these given equations here. So this equation then is for the first plane, and this equation here is for the second plane. And because we're looking to find the acute angle between 2 planes here, we know that we need to use the following result here. So we're going to use them. So we use here cos theta is equal to the modulus then. So we do n1, so that's the normal to the first plane here, and we dot this with the normal to the second plane, which is n2. And this is all over them. The modulus of n1, that's just the normal to the first plane here, and we times this by the modulus then of the normal to the second plane, n2. Okay, like so. So n1 here, that would be I plus 3j minus k, and n2 will be 4i minus j plus 3k. So actually find the angle here between 2 planes. It's pretty straightforward, right? So in that case then, cos theta, what would this give us here? We take the modulus then. So n1 here, that's going to be I plus 3j minus k, right? We do I plus 3j minus k here. And we dot this then with n2 here, which is 4i minus j plus 3k. We have 4i minus j plus 3k. And this is all over them. So we have the modulus of n1 here. So don't forget them. To find the modulus here, this is just the same as finding the magnitude of this normal vector here. And to find the magnitude of a vector, all we do is we use Pythagoras here. So this will be the square root then. We take the square root here. We do 1 squared plus 3 squared plus minus 1 squared. We have 1 squared plus 3 squared plus minus 1 squared, like so. And then we times this here by the square root. So again, all we're going to do here is find the magnitude of the normal to the second plane. So in that case here, that will be 4 squared plus minus 1 squared plus 3 squared. We get 4 squared plus minus 1 squared plus 3 squared. Okay. Let's just simplify this here as we go. So let's start then with the numerator here. So cos theta then is equal to, again, we take the modulus here. So we have the scalar products here, right? So we're going to do 1 times by 4, so that would give me 4. We then do 3 times minus 1, so that would give me minus 3. And then finally we have minus 1 times by 3 here, which again would give us minus 3. And this is all over them. So let's simplify the first square root here. I've got 1 plus 1 plus 9. That's going to be the square root of 11. Get the square root of 11. And then we times this here by the square root of, I've got 16 plus 1 plus 9. So altogether then, we get the square root of 26 here. Okay. And we do need to use the modulus here because if you just notice my numerator here would actually be negative, right? I get minus 2 there. So in that case then, what we get here for cos theta is 2 all over the square root of 11 times the square root of 26. The square root of 11 times the square root of 26 here, like so. And in that case then, if we just want to find theta here, all we do is we take cos inverse of both sides here. So theta is equal to cos inverse. Cos inverse then of 2 all over the square root of 11 times the square root of 26 here. So 2 over square root of 11 times the square root of 26 here, like so. So all we need to do then is just use our calculator here to evaluate this. So in that case then, again, if we just round this to say 1 decimal place here, what we get then for theta is we get 83.2 degrees there. So 83.2 degrees there. Okay. And there we have it. So that gives us the solution there to the very last question, question 2. And that brings the end then of this video here on finding angles between lines and planes.